this new link, so I could move that. First of all, let me just remind you that I put the first week's homework set on the board last time. So there were, like 8 problems or so from Chapter 1. So please make sure that you are aware of the homework. It'll be due next Wednesday. It doesn't matter what kind of paper you use. Any clean paper is fine. You could certainly use engineering paper, but it's expensive, so you don't have to. But anything is fine. If you could avoid writing on both sides, that would be best. It's harder for me to grade it that way, so try to write on one side of the page. Plus, it'll be better for you in the long run. I mean, keep in mind, you're really doing the homework for yourself, not for me. You would like to be able to use your work as you study for exams. And if you just kind of do whatever's minimal, it's not going to help you out when you're studying. I mean, you really want to set up these problems appropriately. I will note that section 11 of chapter 1 goes through basically a little discussion of problem-solving techniques, what you should do as you're solving any of these problems in thermodynamics. I don't know that that's absolutely necessary for these first several problems because they're all pretty short, basic problems. But certainly as we go through the material, that will become more important. I actually plan to cover that in more detail, but not till the beginning of the 4th week when we really start getting into some realistic problems associated with thermodynamics. But that doesn't mean you can't read it now and get a feel for what's generally expected of you when you put together a homework problem. But again, keep in mind it's for you. You are not going to remember doing this problem 10 weeks from now when you're studying for the final exam, right? You want to have problems that are standalone problems that you can just pull out of your notebook and then remember that you've done them. Start by writing the problem out, or these days you can just scan it or photo it and print it out on the page, so that begins the problem. Then you would continue by setting up the equations, the data, et cetera, any diagrams, sketches, any assumptions. Again, it's all explained in section 1-11, but keep in mind that it's really important that you learn good problem-solving techniques. When you're doing exams, if I can't understand your problems, how can I give you credit for them, right? So you got to do the best you can. All right, so today is our dull, boring lecture. That's just today, not all the lectures. Mostly they'll be fun. Well, I try to make thermodynamics fun. But the reality is we need to start with a whole bunch of definitions and basic concepts, terminology and all that. And that's what really makes today's lecture probably the most dull and boring of all of our lectures. As usual, if there's any questions, just raise your hands. Although I don't know that I'll even be looking at the classroom a whole lot just because of all this other stuff around me. So if I don't see you right away, just, cough, clear your throat, say excuse me, whatever it takes. I just don't want to leave anybody behind, especially you guys on this side. I mean, I kind of have to point this way because that's where my whiteboard is. So, okay. So let's begin with some definitions, and we'll start with the system. Okay, so anything we analyze will be the system. And basically this is just defined as a quantity of matter to be studied. Let me also remind you that my handwriting is often pretty poor. This might not be too bad. I find that with a whiteboard, the board's so slick, the pen is so slick that my hand just moves wherever it wants, and my whiteboard writing is really, really bad. So this actually is about as neat as it gets. So we're going to be studying systems. All right? And there's 2 types of systems. One we would call a closed system. Oh, I'm sorry, one other thing I needed to mention before I start, or as I start. It turns out that MediaVision is making the video of this lecture available to me every day right after the lecture. I mean, not immediately, but within an hour or 2. And I will give you a link to that. I don't have it right here with me. It's probably on my iPad somewhere. I guess I could hunt for it. But so you should be able to access that link anytime you want to. So if you're not really clear on what I'm writing, or if you're falling a little behind in your notes, then you should be able to make up for it. I will make that link available to you. Although I will note that the link is really for this class. It's not being made available to the general public. There may be issues, accessibility issues or other issues, which would make it so that I can't really, make it available to everybody yet. But if it's a lecture you're listening to, then I should be able to, make it available to you, and they said I can. So if I don't remember to do it by the end of the day, then I will make sure that on Monday I give you that link so you can look at these lectures. By the way, the lectures don't seem to work on like iPads and stuff. I think you actually have to have a real computer, and it has, I don't know, Silverlight or whatever that other plugin is, some Adobe Flash plugin or something, and I don't think you get those on the flat devices. So anyway, closed system. So when we talk about a closed system, basically it's a quantity of mass that we will study. Let's just call it a fixed quantity of mass. Okay. The other type of system that we're going to be dealing with is called the open system. And an open system can also be called the control volume. Another thing too, this paper isn't exactly fixed. Last week it was fixed to the table and I just had to rip one off the top of the pad. Today they're not fixed, so it looks like it's sliding all around. So if it slides off and I don't notice it, please help me, okay? Anyway, an open system, which can also be called a control volume, is basically a fixed volume, if you will, that we're going to be studying. So as the names imply, if we have something like, let's say, a tank, where we're simply going to be analyzing the substance in that tank. I mean, the tank is sealed, it's rigid. It doesn't even have to be a tank. It could be like a piston cylinder device. But if it's a sealed device, then those are closed systems. But if it's something that involves flow, like a pump, where we're going to be moving a fluid or a gas, a liquid through the pump, or a turbine or a compressor, clearly you don't have a fixed mass. The mass is flowing. So that we would analyze as the open system, a fixed volume, if you will. Okay. We also have to understand that systems have boundaries. Okay. The boundary basically just represents the interface between our system and what's outside of the system, which is what we would call the environment or the surroundings. So all systems are going to have some sort of a boundary. It turns out that's important. If we have a system, we're not concerned about what's happening really within that system. We're really concerned about what's happening between the system and whatever that system is working with, that is, whatever the surroundings are. So all systems have a boundary. Outside of the boundary is the surroundings, or we can call it the environment. Okay, so maybe I should just kind of underline some of these things that are important. Okay. Now, when we're dealing with these systems, we will always be dealing with systems here. It's important to know where the boundary is, but usually it's going to be obvious. If we're talking about a tank, the boundary is the wall of the tank. If we're talking about a pump, the boundary is the wall of the pump. If we're talking about a piston cylinder type of a device, then the boundary is, the inside, well, not inside, the edge of that piston and cylinder. So it should never be a problem to identify where the system ends and where the surroundings begin. I mean, it should be very, very obvious. Another thing that one might note is that there will be transfers at the boundary. Not always, sometimes. So there will be transfers of heat or work sometimes mass. And again, it depends on the problem as to whether these will actually occur. But we're specifically interested in these transfers. If we're adding heat to water that's inside a tank, we need to know how much heat that is so that we can figure out what's going to happen to the water that's inside that tank. So we need to understand where the boundary is. We need to understand that there will be transfers of heat, work, or mass at the boundary. Okay. I might also note that heat and work are both energy transfers. Okay. Mass obviously is mass that's moving in or out, but heat and work are forms of energy, and that's something that we're going to certainly talk about in a lot more detail. Now, another thing that we need to deal with where'd the lines go? No lines. Reject. Yeah, I think this will work out okay. I'm wondering, this is to the technician in the back, is it possible to make more of the screen, actually to go the other direction, so that pretty much everything that's written on one page covers the whole screen, instead of like, I mean, can you do it the other way? I mean, zoom in. Yeah, zoom in. Oh, to closer? Yeah. I mean, I don't know. Yeah, something like that. Yeah, that works better because then, everything is a little bit bigger, and I think it'll be a little bit easier to see. Okay. All right, so one thing we also need to do is make sure that when I draw things, you understand what I'm drawing. So let's just say that we're dealing with a closed system. Okay. When we deal with a closed system, the system boundary is always going to be shown as a solid line. And this is really just for consistency. If we have any kind of transfers at the boundary, then they're going to be shown, right? If we have heat transfer, I'll put a Q. Q actually is going to stand for heat. If there's work, then I'll put a W for work, et cetera, et cetera. So when I solve any kind of a problem for any system, it doesn't matter whether it's open or closed really, I'm always going to illustrate it appropriately. I'm going to use arrows to indicate whether heat goes in or out, work goes in or out. You can kind of see here that Q pointing towards the system really implies that heat is going into the system. The other one, the work, the arrow going out implies that work is going out of the system. In other words, the system is doing work to its surroundings. So I'm going to try to be very consistent with regards to the diagrams. And then on the other hand, if we have an open system, then open systems are going to be shown with a dashed line. So, I mean, that's a kind of a typical symbol for a pump. So let's just say that's a pump. The dashed line is going to represent the boundary. But again, this is for an open system, right? So, make sure that when you're solving problems, you do essentially the same thing. Again, it's really just for consistency. Now, do you absolutely have to do this? No, you really don't, but it would certainly be best if we were all consistent. It'll certainly make it easier as you're solving problems and as I grade problems. Okay. All right, so now another thing that needs to be noted. When we deal with thermodynamics, especially in your first several courses in thermodynamics, the systems that we're going to analyze are somewhat idealized. In this class, the systems we're going to be talking about are what we call simple compressible systems. So when we talk about a simple compressible system, we're going to neglect any external forces such as electrical forces, magnetic forces, gravitational forces, the forces due to motion, surface tension forces. That's the nature of our simple compressible system, okay? We're only concerned about what's happening in the system. We're not concerned about some of these random forces that might be applied. Now, that doesn't mean that we're never going to have to solve problems that involve magnetic forces or surface tension or electrical forces, but in general, we're not. Once we start considering all these other types of forces, then it just greatly complicates the problem. And in your first course in thermodynamics, it's just not worth it to do that, especially when you consider that these other forces that I've just mentioned are generally going to be very, very small, if not entirely negligible, or even non-existent for most problems. Like if I'm heating up a cup of water inside, or maybe just adding work to a piston cylinder device, or just anything like that, there's no electrical forces involved with that, right? There's no magnetic forces. I mean, these kind of forces just don't exist. So when we talk about the simple compressible system, we're basically, again, we just neglect external forces such as electrical, magnetic, gravitational, surface tension, motion, forces. Okay, so again, all of our systems are going to be simple compressible systems that we're going to deal with in this class. Okay. Oh, yeah, thank you. Okay. So all our systems are like this. Okay, it is a simplification, but it's not a simplification that adds any inaccuracy into our problem solving. Okay. All right. So, again, still trying to get used to this. All right, so next, energy. Remember again, today is just a day to define a bunch of terms and discuss general concepts. So not too exciting. So now we talk about energy. I think we're all familiar with the concept of energy. I mean, we hear about it all the time. I think we understand what energy is. Basically, we think of energy as the ability to produce work or to exchange heat. That's all energy is. All the problems that we analyze, almost without exception, are going to involve some energy transfer, okay? So we need to understand what energy is. Now we would note that energy can either be stored internal to our system or it can be transferred. Okay. Now, keep in mind that we're not really concerned about the modes in which the energy is stored or which the energy is transferred, at least not in this class. We're really only concerned about how much. You know, we want to know how much energy is stored within our cup of water or whatever it is we're analyzing, right? We want to know how much energy is added to that cup of water or is removed from that cup of water. We need to know how much work that water is doing onto its surroundings. We're not concerned with the mode through which this takes place. Now, you will certainly take other courses, like your heat transfer class, where you'll learn in a whole lot more detail about the nature of heat transfer and different forms of heat transfer. You know, you probably have already had your dynamics class, at least many of you have. You'll learn more about work and the nature of work and how work is transferred. But in this class, we're not concerned with any of that. So all we really concern ourselves with now is trying to quantify the energy. You know, how much is going to be stored, how much of it is going to be transferred. Let's also note that when we talk about energy transfer, it's only going to be transferred in two possible ways, either as heat or work, right? So energy can be stored internal to our system, or it can be transferred as heat or work. Now, eventually we're going to talk about the first law of thermodynamics, and that'll allow us to keep track of how much energy is stored versus how much energy is transferred, but that's still in the future. Okay? So, you know, when we're heating up a liquid, we're only concerned about how much heat we have to add by heating up that liquid. We're not concerned about what's happening to the molecules as they interact with each other, and, you know, the actual modes of heat transfer. It has nothing to do with what we're going to be covering in this particular class. Okay? Now, any substance that we deal with is going to have a collection of properties. Oh yeah, I'm going to underline things here and there. Okay. So what are these properties that we are going to be dealing with? Well, there's a lot of them. First, I might note that when we talk about a property, we're talking about an identified, observed characteristic. Okay, so any substance will have a collection of properties. An identified, observed characteristic. Okay. I might note that some of these characteristics are going to be measurable and some are not going to be measurable. I kind of alluded to this last time. I mean, something like temperature, we have a device called a thermometer or others that we can actually use to measure that temperature. But there's also a property that's called internal energy. There's actually a certain amount of internal energy that's going to be held by any substance at any particular point in time, but there's no such thing as an energy meter. We don't have a device we just stick in our cup of water and it says, oh yeah, that's how much energy is in this water. So these are certainly identified, observed characteristics, but they're not always measurable. And one of the things that we're going to have to figure out right away is how do we find the non-measurable properties that are going to be used in problem-solving analysis when all we have is data based on measurable properties. I mean, can I take temperature and pressure data, maybe density data? You know, density is just mass and mass divided by volume. Can I take that data and somehow get all the other data that we're going to need? Well, the answer is, of course, yes. Well, not of course, yes. The answer is yes. But it's just something you have to be aware of. Some measurable, some not. But that really shouldn't matter to us. We just have to understand that these properties exist. Okay? Now, any set of properties that a substance has is called its state. So a substance's set of properties is called its state. Okay? So if we have a collection of properties, it will have a certain state. If we say that a substance exists at a certain state, it therefore has a certain collection of properties. What we need to understand, though, and this is one of those rather interesting things about our simple compressible system, is if we know any two of a certain type of property, that sets the whole state. Okay? There's a countless number of thermodynamic properties, I mean at least 6 major ones. I don't need to know all 6 of them at any one point in time. If I know just 2 of them, then having any 2, all the others are going to be set. But there are certain restrictions here. So I'll note here that the state of a simple compressible system again, my writing is kind of sloppy. That says simple compressible, even though it doesn't look like it. The state of a simple, I better rewrite it. The state of a simple compressible system can be determined by knowing, again, my writing is sloppy. by knowing any two, and again, I said there's certain types. By knowing any two what are called independent intensive properties. Okay. Now, we have to talk about, well, what do I mean by independent intensive properties? And I think we'll just start with independent. Some properties are dependent on other properties. I mean, for instance, let's say we have water that's boiling into steam at standard atmospheric pressure at sea level. We know, because we've all cooked before, at least boiled water, that that happens at exactly 212 degrees. Turns out that water at standard atmospheric pressure, which is 14.7 pounds per square inch, always boils at 212 degrees. They're not independent. The only possible temperature for water to boil at standard atmospheric pressure is 212 degrees. They're dependent upon each other. The same thing goes with water when it's freezing into ice, right? Water freezes at exactly 32 degrees Fahrenheit, or 0 Celsius if you prefer that set of units. No other temperature, right? It's always at 0 degrees Celsius. Now that'll change if we change the pressure. If we go up into the mountains, let's say we're up at Big Bear, the standard atmospheric pressure is maybe 13.5 pounds per square inch instead of 14.7. Well, water's always going to boil at a slightly lower temperature, probably about 180 or 185 degrees Fahrenheit, always, without exception. So pressure and temperature are not independent variables all the time. So sometimes we find that there are properties that are simply dependent upon each other. By the way, that's why it takes longer to cook your spaghetti when you're up in the mountains. Water's not boiling at 212 anymore. It's boiling at something less than 190 degrees. Of course it takes longer to boil. It's cooking at a lower temperature, right? Well, anyway, things to learn about in thermodynamics. Okay, so simple compressible system can be determined by knowing any two independent intensive properties. What is meant by intensive property? An intensive property is one that does not depend upon its size. Okay. For instance, temperature is an intensive property. I mean, we know that, even though we don't know that we know that. We have a cup of water, right? And that cup of water is, let's say, at 70 degrees Fahrenheit. I can look at the whole cup, and it's going to be at 70. I could take a tablespoon out of it, and it's going to be at 70. I can take a drop out of that. It's going to be at 70. I could take a little tiny little piece out of that drop. It's still going to be at 70. It doesn't depend on whether I have a whole cup or just a little tiny bit. The temperature is the temperature. So temperature is an intensive property. The same thing with pressure, right? The pressure of that cup of water, again, at standard atmospheric pressure is 14.7 pounds per square inch. I can take a spoonful out. I can take a drop out. It's going to be at the same pressure, right? The same thing with density, right? The density of the water doesn't change simply because I have a whole cup of it versus a little drop of it. If that water exists right here on this tabletop, the density is always the same. So temperature, pressure, density, these are all intensive properties. Yes?
If the pressure doesn't change, how come at really low depths and the deep ocean, their pressure is much higher if you were to submerge a submarine?
Oh, I didn't say the pressure doesn't change if you move around. I mean, if you move around in the gravitational field, it will certainly change. If you're up at Big Bear, the pressure's lower. If you're in the ocean, the pressure's going to be quite a bit higher because you have that many more feet or perhaps miles of atmosphere plus ocean above you. I'm just saying that if we took like a cup of water, let's say from the deep ocean at a huge pressure, a little spoon of that water is going to have the same pressure as does the whole cup, as does a little drop of the water, as long as it's the same water coming from the same depths in the ocean. So yeah, certainly as we move around, you'll have different pressures for different substances. But as a property goes, pressure does not depend upon the quantity. It doesn't depend on the size. It just depends on really where it is. Okay, anyway, I'm just defining some of these terms. Okay, so temperature, pressure, density, those are intensive properties. Okay, now there's another type of property that's called an extensive property. Oh, yeah. Thank you. So extensive properties, it does depend on the size. Okay. So for instance, volume. That's kind of obvious because volume is the size. If I have a cup of water, the volume is a cup, 250 milliliters, right? If I take a tablespoon out of that, well, now I have a smaller volume. So clearly volume is something that does depend upon the size. What about the internal energy? U is internal energy. Remember I said how energy can either be stored internal to the system. Well, that energy that's stored internal is called internal energy. So that certainly depends upon the size, right? If we have a whole cup of water, there's a lot of energy in that cup of water. If I have a little drop of it, there's not a whole lot of energy in it because it's a much smaller quantity of it. So volume would be an extensive property. Internal energy would be an extensive property. And these are just a couple of examples. We'll learn about more of them as we go through time. Oh, yep. Okay. There we go. All right, so we know something a little bit more about properties now. Now, there's another type of property that we should be aware of. And this is what we'll just call a specific property. A specific property, a specific property is actually an extensive property, but per unit mass. Again, sloppy writing. Okay. So probably the best example of that would be what we'll call specific volume. If I were to take volume and divide it by the mass, lowercase m here is going to be mass in this particular course. So if I take the total volume and divide it by the mass, that's what we would call specific volume. And in fact, we give it still the letter V, but it's going to be the lowercase letter v. Now, it's hard for me to make a distinction between a capital letter V and a lowercase letter v. In the textbook, it's easy. They just use boldface print for capital V and normal print for lowercase letter v. But I can't really do that. So I've used kind of a pointy bottom with a little curve on it. It really looks more like the Greek letter nu, doesn't it? But this is my lowercase letter v. And that is what we call the specific volume. Okay. I can do the same thing for internal energy. I can take the total internal energy and divide it by the mass, and I get a lowercase u. So I'm going to try to put my lowercase u's, they're going to have like a little wing off the bottom of them, again, to make a distinction between a capital letter and a lowercase letter. If capital letter U is the internal energy, we could even call it total internal energy, then lowercase u is the internal energy per unit mass. We would call it specific internal energy. Okay, so what's important here is to note that specific properties are also intensive properties. Okay, I mean, let's just think about it, and I'll use specific volume as an example. What is density? Density is mass per unit volume, right? Pounds per cubic foot, kilograms per cubic meter. Isn't the density an intensive property? Right, we talked about that before. But isn't the specific volume just the inverse of the density? If density is mass per unit volume, then specific volume is volume per unit mass. They're the same variable, they're just the inverse of one another. If one of them is an intensive property, like as is density, then the other one has to be an intensive property too. It doesn't depend upon the quantity, right? If I have a cup of water, it'll have its own density, or if you will, its own specific volume, the inverse of the other. If I take a little spoon of that, it'll have the same density as the whole cup of water did. Its inverse is going to be also the same specific volume. So you can see just by this example that the specific volume is actually an intensive property. It doesn't matter how much you have. You can take a cup of that water, a spoon out of that, a drop out of that, and the specific volume is not going to change. The density is not going to change. I mean, it can change if you do something to it, if it undergoes some process. But as it is in that cup of water, it doesn't matter whether you're analyzing the whole cup or just a piece of that cup. The density, therefore the specific volume, doesn't change. So these terms, specific terms, are also intensive. So let's show that. That specific properties are intensive properties. So when you're trying to solve a problem, whatever that problem may be, you need to know two intensive properties. Those intensive properties can be things like temperature or pressure, but they can also be such things as the specific properties, like the specific internal energy or the specific volume. But again, we need to know any two of these intensive properties. If we know any two of them, all the others are known. Okay? They're tabulated in the book. In fact, that's what this set of tables is in the back of your textbook. If you know any two properties, you just go into those tables, I should say, any two intensive properties, you just go into those tables and you can look up all the other properties you would ever want or need. Was there a question?
Yeah. Are specific properties intensive or extensive?
No, they are intensive. Specific properties are intensive properties.
Said extensive properties.
Uh-oh, did I say it wrong?
No, they're made of extensive
You
properties,
take
and
an
when you do that,
extensive
you turn them
property
into
and make it create
intensive.
a path,
Right.
create a mass that makes it intensive.
Right. If you have an extensive property and you divide it by the mass, that's what this is. You divide it by mass. So extensive property per unit mass, right? So if you have an extensive property per unit mass, in other words, if you divide it by the mass, then it becomes an intensive property. So this is what we observe as we observe the nature of different substances and their various properties. Okay. Now, any further questions? All right. I mean, it might sound a little bit complicated at first here, but you know, it gets more understandable over time. At least I hope it does. All right. The next thing we need to note is that if all the intensive properties are the same over time, then we say that our system is in equilibrium. So if the intensive properties do not change over time, the system is in equilibrium. Okay. And in fact, all of the problems that we're going to solve are going to be problems that involve equilibrium. Okay. If we look at that cup of water, it's just going to have one set of properties. It'll have a certain temperature, it'll have a certain density or specific volume, it'll have a certain pressure, it'll have a certain amount of internal energy associated with it. If those things don't change over time, then the system is considered to be in equilibrium. Now, things will change over time. I mean, when we look at a substance just sitting there in a jar, in a cup, in a bucket, whatever, we're always going to assume that it's in equilibrium. But it will eventually undergo some process. I mean, we're not going to just stare at substances all day that don't change. I mean, we're going to undergo processes, right? We're going to look at that tank and we're going to add heat to it. And all of a sudden the temperature and the pressure are not going to be the same anymore. The density might not be the same anymore. So these are things that we're going to have to consider. But at any particular point in time, the system is always considered to be in equilibrium. There's two types of equilibrium. We have one that's called mechanical equilibrium. And basically, if we have mechanical equilibrium, there's no unbalanced forces. Okay? If you put a force or if you put pressure on a substance, something's going to change, right? If you put pressure, let's say you have a balloon and you put pressure on it, then the pressure will change, right? If you push on it, its pressure changes, so it's not in equilibrium anymore. if it's a mechanical equilibrium, it means there's no unbalanced forces. The force, let's say, of the atmosphere pushing on the balloon is exactly the same as the force of the air in the balloon pushing back on the atmosphere. That's basically a form of mechanical equilibrium. So if we have mechanical equilibrium, then there are no unbalanced forces. We can also have what's called thermal equilibrium. And in thermal equilibrium, there's no temperature differences. Okay? In other words, there's no difference between the temperature of, let's say, the air in the balloon and the temperature of the air surrounding the balloon. So that would be a statement of thermal equilibrium. Okay? There's no temperature differences. Okay? And if we have both thermal and mechanical equilibrium, then we often use the word thermodynamic equilibrium. And quite frankly, rarely do we look at a problem that's in thermal equilibrium and not mechanical equilibrium, or only mechanical and not thermal equilibrium. We're just looking at substances that are going to undergo certain processes, and they're always just going to be in equilibrium. Okay? The equilibrium will be both thermal and mechanical. There's no imbalanced forces. There's no temperature differences. So if we have both mechanical and thermal equilibrium, we have what's called thermodynamic equilibrium. Now, the whole idea of thermodynamic equilibrium is kind of idealized. It's not always realistic. Maybe the best way to explain this is as follows. We are going to analyze processes. Okay? Let's say we have a piston cylinder device. Maybe it's part of an internal combustion engine. And we have some substance, let's say it's air inside that piston cylinder device, and we push on the piston. That's a process that takes place. We're going to start with one set of properties. We're pushing on the piston. We're going to end with a different set of properties, right? You know, maybe the pressure is going to go up. Maybe the temperature is going to rise. But we're going to actually start in an equilibrium state, and we're going to then move through what clearly is not an equilibrium state because we have this imbalance between the forces of the piston and the air that's inside that piston. How do we get around that? Well, what we're going to have to do in this class is recognize that the processes that we analyze are always assumed to go in infinitesimally small steps over an infinite period of time. Now, it's not particularly realistic, but at least in doing so, you kind of guarantee that you're always at equilibrium. You're going so slow in such small steps that for all intents and purposes, you're always going to be in equilibrium. In the real world, processes don't occur that way, and you don't always have equilibrium. Okay? Equilibrium is something that takes time to occur, but we'll just assume that we're always going to be in equilibrium anyway. And again, this is just a simplification that we're going to have to realize for this class. So anyway, if we have both mechanical and thermal equilibrium, we have thermodynamic equilibrium. Sometimes we just use the phrase equilibrium without any modifiers. We're always going to be in equilibrium as we go through our class. Okay. Now, I might note at this point that there are other forms of equilibrium as well. We could have chemical equilibrium. We could have electrical equilibrium. Well, we're ignoring all that. We're assuming that there's no electrical forces. We're assuming there's no chemical reactions. I mean, this is all part of that whole idea of the simple compressible system. We're only dealing with heat transfer, dealing with work. We're not dealing with any of these other forces that largely we're going to ignore anyway. All right. So moving on. So now let's look at process. If a property, and thus the state, changes, then a process has occurred. So we are always, well, at first we're just going to understand the whole nature of equilibrium. We're just going to look at a cup of water, or we're just going to look at a certain amount of air or something like that. We're not going to even deal with any processes. But after we get, a good understanding of the nature of thermodynamic properties and how to get the data, then we're going to start looking at processes. And it should be noted that the processes, again, as I mentioned a moment ago, are always going to occur in tiny increments over a long period of time. So they're always going to remain, that is, the system is always going to remain in equilibrium, and we actually call that a quasi-equilibrium process. So if a property, and thus the state, changes, then a process has occurred. In this class, and in fact in all beginning classes in thermodynamics, the processes occur very slowly, such that we are always in equilibrium. And this is basically called a quasi-equilibrium process. Some people call it quasi-equilibrium. Yep. Thank you. Anyway, this is called the quasi-equilibrium process. So all of our processes are going to occur that way. Okay. They occur in tiny increments. Now, sometimes as we undergo processes, we find that certain properties are going to remain constant. So if a property remains constant during a process, then we use the prefix iso. Okay, so for instance, if we undergo some process and the temperature remains constant, we use the word isothermal process, thermal implying temperature. If we have a process where the volume remains constant, like let's say we have a tank, sealed rigid tank, no matter what you do to that, it's still a sealed rigid tank, right? It has to have the same volume. We don't use the word isovolume. We call it an isochoric process. I guess choric must be Latin for volume or something like that. If we have a process that occurs at constant pressure, like let's say we have a vertical piston cylinder device such that the weight of the piston being constant, acting through a constant area because it is a piston cylinder device, no matter what happens inside the cylinder, the weight of that piston is such that it's going to always maintain a constant pressure in that system. We call that isobaric process. So we use the prefix iso to identify processes where something stays constant. Okay. Again, isothermal for constant temperature, isochoric for constant volume, isobaric for constant pressure. Anyway, this is just something to be aware of. Again, we're just talking about basic concepts and trying to make sure we understand, the terminology for this particular class. All right, moving on. The next thing I want to identify is what's called the cycle. If we have a process that begins and ends at the same state, we call it a cycle. Okay, so cycles are actually pretty common. We talked about 2 cycles last time, right? Just as an introduction. One was that refrigeration cycle, and one was the power plant cycle. We start at one state, we go through various processes, and we get right back to the same state again. So that's called a cycle. So we'll be talking about various cycles in this particular class. Another term to define is called a steady flow process. So a steady flow process is one that does not change over time. That doesn't mean it's a cycle necessarily, right? When we talk about a steady flow process, we'll talk, let's say, about a pump. Okay, the fluid goes into the pump, work is done on that fluid by the motor connected to the pump, fluid goes out of that pump. If that pump stays the same all the time, if the pressure and temperature of the water going into that pump is always exactly the same, if the pressure and temperature of the water coming out of that pump is always the same, over time, we could look at that pump today, tomorrow, next year. That would be a steady flow process because there's no changes over time. That has nothing to do with whether we begin and end at the same state. We're really talking about changes over time here. So steady flow processes are also processes that we will be analyzing. Clearly, these apply to the open systems, not the closed systems, right? Closed systems are those of fixed mass. So we're not dealing with something that's going to remain constant over time. All right, so these are just some of the basic terms we're going to deal with. The next thing that I'm going to talk about has to do with units. Now, I mentioned before that we're going to use both the British system of units. I always call it British, but most people call it the English system of units. Although, oh yeah, thank you. Although I would note that the Scottish had just as much to do with the early developments in science, and it's really more appropriate to call it British rather than English anyway. Anyway, just a call out to the Scots, right? So we have two different sets of units that we're going to use. We've got the British system of units, then we have the standard international set of units. And there's really just four basic terms that form the basis of all the units we're going to use, right? Mass, length, time, and then we also have force. Now in the British units, we're going to use the pound mass. Now, at this point, you've all had statics. Many of you have had dynamics. And you use the slug as the standard unit, right? Who uses a slug? Nobody's ever heard of it before until you got into statics, and nobody will ever use it again after statics, well, except in dynamics. So the pound mass is actually the preferred set of units. But a pound mass is not the same as a slug, okay? If you have an object that has a weight of 1 pound, then we say that its mass is 1 pound mass. On the other hand, if we have an object that has a weight of 1 pound, its mass is what? 1 over 32.2 slugs. So, you know, a slug and a pound mass are not the same. They're different exactly by the acceleration of gravity, but they're not the same. So we just have to understand that the pound mass is our mass unit in the British system of units, all right? That's all you really need to understand. I should note that we have to use a subscript m because the pound mass is not the same as a pound force, which is our force unit. Certainly something that weighs 1 pound will have a mass of 1 pound, so there's that equivalence, but they're not the same. One is a mass unit, one is a force unit, and they're different. So the length unit in the British system is typically feet, the time unit is the second, and the force unit is the pound force. Again, just because there's this equivalence based on the weight, we can't just arbitrarily turn pounds masses into pounds force. If you have a problem and the units are pounds mass, then that's a mass unit. You can't just change that to pounds force because you want to. It's totally different. They both use lb for pound, which I have no idea where that ever came from. But the F for force, the M for mass. Yes?
Maybe getting ahead, but like we convert by using the same 32.2.
We're never going to have to convert because we're never going to use slugs. So you do not convert from mass units to force units. They're totally different concepts. You know, a force represents some energy that you're pushing on a system with, right? The mass has to do with, well, with the object's mass. So they're just totally different concepts. So no conversion necessary. They're just two different units. In the SI system, things are a little bit different, right? We use the kilogram typically for mass. The length tends to be the meter. Time is still seconds. The force units are the Newton, right? And I should note that the Newton is the same thing as 1 kilogram meter per second squared. So 1 Newton equals 1 kilogram meter per second squared. Now, can I say that 1 pound force is 1 pound mass foot per second squared? No. A slug? Yeah, a pound force is a slug foot per second squared. But a pound force is not a pound mass foot per second squared. So they're a little bit different again, right? Anyway, these are the standard or traditional units. One thing that I guess we should also talk about is weight. Typically, we don't use weight in a thermodynamics class. We're only going to use mass. But, I'll just talk about weight. First of all, weight is a force. We know that weight just uses capital letter W, and the weight is the mass multiplied by the acceleration of gravity. The acceleration of gravity is either 32.174 feet per second squared, or it's 9.807 meters per second squared. So, sometimes we're going to have to identify an object's weight, but usually we don't. I just like to include it here nonetheless. Okay. Now, when we deal with problems, for most problems, we will be dealing with the mass, but sometimes we have to deal with moles. So let's remember that. So a mole is N. Sometimes we'll just call this the mole number is N. Remember, well, I say remember, but this is something from your chemistry class, right? A mole represents the equivalent number of molar masses. So for instance, if we have water, we know that water has a molar mass of 18, right? It could be either 18 pounds per cubic foot. That's not the right units. Anyway, it's the molar mass. It represents the number, basically the number of particles within the nucleus of that atom, right? Water has 1 hydrogen, 2 hydrogens, 1 oxygen. Each hydrogen has just 1 proton. The oxygen has 8 protons, 8 neutrons. So 16 for the oxygen, 2 for the hydrogen, so a total of 18 units. So 18 is the molar mass for water. If we have 18 pounds of water, then that means we have 1 mole. If we have 36 pounds of water, we have 2 moles. We might want to call it a pound mole. On the other hand, if we have 18 kilograms of water, then that's also 1 mole. We might call it a kilomole. If we have 36 pounds of water, we have 2 moles or kilomoles, et cetera, et cetera. So N is the number of moles. It's just the mass divided by the molar mass. Now, when I was a kid, we used the word molecular weight, not molar mass. I have no idea what your chemistry teachers or physics teachers use. I think, molar mass. I would just call it the molar mass. That's typically what it's called these days. And then again, remember, the lowercase m, maybe I shouldn't say remember. I think I identified it somewhere before. Yeah, the lowercase m is the mass. So the mass per unit mole is, the mass divided by the molar mass is what we call the moles or the mole number. Right? So some problems we have, we're going to need the mole numbers. Some problems we're not going to need the mole numbers. It really just depends. So are there any questions on any of this up until now? Yeah.
We don't jump into how many molecules in a mole, right? Like the Avogadro number at all.
No, we're really only concerned with numbers of units of mass or numbers of moles of any particular substance. Yeah. Okay. So again, these are just terms to review that we should be aware of. Now what I want to do is start looking at some properties. Okay. So some properties. Some of these we've already talked about, some we haven't. First of all, density is one of those properties that we'll often deal with. But let's remember that density is just the inverse of a specific volume. They're both intensive properties. So the specific volume is just the inverse of the density. So this is one of those properties we're going to deal with, and we're going to use it a lot. I mean, density is measurable. We can measure a mass, we can measure a volume. The ratio of the two is the specific volume or density, right? So that's one of those measurable properties. It's going to be really, really useful to us. The units for specific volume are going to be either cubic foot per pound mass, and I like to put my units inside square brackets, or it could be cubic meters per kilogram in the SI units. So the specific volume is one of those units that we're going to deal with. Another unit that we're going to, another property that we're going to deal with. Another property that we're going to deal with is called the molar specific volume. And whenever we have a molar term, we put a little bar over it. Now, no longer is this equal to 1 over the density, but this does relate to the specific volume. If we talk about molar specific volume, instead of the volume per unit mass, it's going to be the volume per unit moles. So this is also something you probably covered in chemistry. So this would be like cubic feet per pound mole, or in the SI units, it could be cubic meters per kilomole. Sometimes a kilomole is just called a kilogram mole. Sometimes you just leave off the E and just write MOL for mole. I don't know, I've always written mole with an E at the end. But that just represents the number of moles. And of course, you could see then that the difference between the two is the molar mass. The units of molar mass is actually mass per unit mole. I'll just write this here above. So you can see then that if we take our specific volume and we multiply by the molar mass, let's see, cubic feet per pound mass times mass per unit mole, that's going to be just cubic feet per mole. So the specific volume is just the molar mass times the molar specific volume. So this is just one of those things that we're going to have to be aware of. You know, most problems we're not concerned with the molar specific properties. Usually we're concerned with the mass specific. Sometimes specific volume is called mass specific volume, and that's just to make a distinction between that and the molar specific volume. Okay, so these are just some of the properties. Now, I don't know, it looks like according to that clock it's 2:04, but according to my watch it's a little bit after 2:05 already. So I think we'll just leave it at this for the time being. We're still talking about some of these basic concepts here, and this is going to continue until next time. I'll talk more about properties. So that's all I have time for today. Remember again that the link that I gave you so you can access your textbook, I forgot the, well, I didn't forget, I didn't even know till today, I forgot the 2017-1, so I had put that on the board here right at the beginning. So please make sure that when you're trying to access that, you use that. Somebody told me that you can get 2 free weeks of the book just as a trial or something like that. So, you know, maybe you just want to kind of go that way and try it to see if you like the electronic book. But you're going to need a book anyway. I mean, you definitely are going to need a book. So it wouldn't hurt to just buy what you're comfortable with. You know, buy the electronic version if that's what you like. So have a good weekend, everybody. See you all next time.